Okay.
Okay, so we are waiting for your slides. So takes few. Yes, so it's okay. We see your screen. So I will tell you when 3 minutes are left. Okay.
Thank you. So can you see my slides too?
Yes, we see them.
Okay, thank you.
You can start.
So, okay. Well, hello. Thanks everyone for joining us today. My name is Fernanda Kleber, and I will give you a very short review about my thesis project, which involved the study of angular momentum effects in supernova progenitors for long gamma ray bursts and the evolution of a relativistic jet through these massive progenitors using three-dimensional simulations. So, well, sorry. Mm, Oh, okay. I think Fabio talked a little bit about some features of our long ERVs. So I will give you a very quick introduction about this phenomena. So, well, long gamma ray bursts are high energy astrophysical phenomena, and also they are thought to be the result of a massive star death. And the most remarkable candidate are the Wolf-Rayet stars, which has a very important lack of hydrogen in its envelope and also have a very low metallicity. So a very important feature about these models are the rapid rotation. So in the theoretical background, some progenitor profiles were proposed by William Heger back in 2006, but also for the study of angular momentum. There have been previous studies, particularly about this topic, made by Geng and my advisor, Lopez Camara, Meder and Meynet, among others. So some open issues about these studies are taking into account different angular momentum distributions. So this is the main point of my project. So, okay. So next, I list here some of the main objectives for this project, which were to propose different angular momentum distributions, combine them, and compare the effects in the progenitors morphology. Also, we chose two representative models to inject a relativistic jet and also follow up its evolution. So we could find some differences between these models and the structural dynamics of this jet. So, okay. So very quickly, I will talk about the theoretical framework for these simulations. I use the Flash code in its 4.3 version, which has a very well-studied relativistic hydrodynamics model. And also I performed these simulations using three-dimensional Cartesian coordinates. So next, for the long GRB's background, as I said before, William Heger proposed a very important progenitor models. So for these simulations, I interpolate into a 3D map the 6TTI model, which is the most studied pre-supernova progenitor. And also, as Diego said before, there are some settings about the relativistic jet that are very common in simulations, such as this luminosity 10 to the 50. And for long GRBs, it's important this opening angle of 10 degrees. And also, it's very common in some studies to apply an injection radius of 10 to the 9 centimeters from the core of the star, so we can avoid the general relativity effects for this study. And finally, the most important point, the angular momentum. So I applied some of the main results for the previous studies, such as the decomposition of the angular momentum into radial and polar coordinates. So this way we could apply a rigid body rotation approximation, and also very important, several distributions for the polar angular momentum. So this is the general theoretical basis. So I will show you here some of the main results from these simulations. What I show you here is the initial condition for these simulations. These are the 3D density contours for the 16Ti model. And also, as you can see here in these arrows, I plot also the velocity field due to the angular momentum implementation. So this is the overall initial condition for all the models. And next, I took some slides for 6 models that we performed the simulations. And what I show you here are the evolution of the morphology of these progenitors at 10 seconds of evolution. So I want you to notice that in the left panel, I show you 3 different models with different angular velocity values. And also in these models, an oblate shape is reached since the expansion of the equatorial radius of the progenitor. On the other hand, on the right panel, what I show you here are the 3 different polar angular momentum distributions that I applied for the simulations. So the differences here are we have 2 components, an oblate one and a prolate one. And this deformation is due to the coupled effects of the radial and the polar rotation. So I think it's quite interesting to know the differences in the morphology for the 6 models. So for this study, we chose, as I said before, 2 representative models, and we inject a relativistic jet. So because of time issues, I will show you only a comparison between a non-rotating model against one of the rotational models. So before that, what I show you in this figure is a 3D map showing the evolution of the jet with the Lorentz factor contours. And also this blue volume show the progenitor's density and also the velocity field for the progenitor. So this is an example only for the jet evolution. So finally, as I said, I will show you a comparison very quickly of a non-rotating model and a model with polar angular momentum distribution, which is linear. So I want to highlight some differences between these 2 models. First of all, the breakout time. As you can see, for a non-rotating model, we have a higher value of the breakout time of the jet, which is the time the jet breakout from the surface of the progenitor. So I want to give a quick explanation about these phenomena of the breakout time from these models. So the elongation of the star triggers the expansion of the inner layers, so the cocoon radius of the jet opens. And this allows the jet to have an easier propagation, and this leads to, and this diminishes the breakout time of the jet. So also, as you can see, I put in these figures the Lorentz factor contours, and this is the maximum Lorentz factor reached by the jet, and this is the value for the rotating model. And as you can see, there are differences also, but this is the same explanation, the easier propagation of the jet because of the angular momentum. So, okay. So finally, I list here some conclusions, and I think the most important one is that we could apply these angular momentum settings in a 3-dimensional simulation, and also we achieve different morphologies in the progenitor's profile, which led to the injection of the jet, and we could study the overall morphology and the evolution of this jet. And also, as you could see, there are some differences between the physical features of these jets. So such as the record time, the maximum Lorentz factor values, and the cocoon radius. So finally, some future studies that could be interesting could be to apply different radial angular momentum profiles instead of polar angular ones, and also to study different launching radius, which affects the record time of the jet 2, and also very important, the variability of the jet, such the pulsation of the precession of the jet. So, well, I think that that's pretty much it. And thank you, everyone. And let me know if you have any questions. Oh,
Thank
sorry.
you, Fernanda.
Oh, sorry.
So we have time for questions. I don't see, well, any question on the conversation panel. So if someone wants to ask a question, please proceed. Okay, so in any case, we have time to discuss after, I guess. And if you have any question, you can use a conversation panel to exchange with Fernanda. Thank you, Fernanda.
Thank you.
So the next talk is one of Nissim Freja.